Alright, welcome back everyone. What we're going to do here is a quick little review for exam number 2. Let's start off with what exam number 2, an overview of what this exam is all about. So you can start this exam. It'll be available anytime between 5 a.m. Wednesday and 5 p.m. Friday. Just be aware that when you start it, you only have a 50-minute time frame, so make sure you're in a nice quiet area free of distractions, so when you get going you'll be uninterrupted for the full 50 minutes. I anticipate the length to be similar to last time, so there's probably going to be between 35 and 45 questions, and those questions will consist of mainly multiple choice problems. There might be a couple true false, but that's going to be it as far as the type of problems. Just like last time, this is open notes and open book, but you can't search for any answers on the internet, and you also cannot collaborate with others in the class or outside the class. So with that in mind, let's move on to the content that's covered in the course, or in this exam. The first subject we talked about were ferrous and non-ferrous metals. And the first topic you should be familiar with, or you should know about, would be the differences in examples of pure metals and alloys. So remember, pure metals are what you find on the periodic table with iron and aluminum, and alloys is the mixture of those elements, or of those pure metals. So the second thing that you should be familiar with is the difference between ferrous and non-ferrous metals and what makes them different. And really it's just the iron, right? The amount of iron, or actually any iron, would make it a ferrous versus a non-ferrous. Also know the difference between steel and cast iron. And as a quick reminder, the main difference, or the real difference, is the amount of carbon involved, with cast iron having much higher carbon content, and that's what gives cast iron its properties of being brittle but hard, versus steel being softer and more malleable. Also know the differences between low, medium, and high carbon steels. Also, non-ferrous alloy types, compositions, and properties. So on the other side of the chart with our non-ferrous. And last but not least, we also have our types of stainless steels and the properties of those stainless steels. All of this is laid out in the notes. So what I think would be beneficial is to have these notes handy. I mean, it's basically just one big page, right? And we can see everything that I just was referencing. So we have pure metals versus alloys, was what we talked about in the very beginning of that lecture. Ferrous versus non-ferrous. We're talking about our breakdown of our either iron-based or non-iron-based, so that first division within this table or chart, right? We have steel versus cast iron, so our next division based on the amount of carbon. And then we had differences between low, medium, and high carbon steels down there. Different types of cast iron and properties of each. So cast irons were down our other side. We have cast iron, gray cast iron, white cast iron. Non-ferrous alloy types, compositions, and properties. So on the non-ferrous side, now we're talking about brass, bronze, solder. What are the properties? Things like that. Types of stainless steel down here at the bottom. So we have ferritic, austenitic, martensitic, and miraging. Alright, so let's move on to the second topic we talked about with torsion, or a twisting force. And with torsion, the idea was that if we have a circular cross section, that's the only thing we talked about, and we apply a torque, so we're twisting it with some torque, T, what happens is we get a stress, and on one side our stress is going this way, and on the other side it's going the other way, linear in between, zero in the center. So it the further away we are from the center, the stronger this stress is, and that stress we label as tau because it is a shear stress. And we developed an equation for this shear stress. We just gave the equation. We said that tau, the shear stress, is equal to, we said T rho over J or TC over J. I'm going to write it yet another way. It all means the same thing, but TR over J, because I feel like these variables might be throwing some people. R is just our radius or our distance away from the center, right? So maybe that's just, I don't want anyone to freak out just because it's a variable. So maybe TR, T rho, TC, they all mean the same thing. In this equation, we have this tau, which is the shear stress, and units on that would be either in pounds per square inch or kips per square inch. Remember, a kip is just 1,000 pounds, and it's all based on the torque. If the torque, which is T, is given in pounds, then we have PSI. If the torque is given in kips, which is 1,000 pounds, then we have KSI. So it's, don't let that freak you out or anything. We just came up with this R being the radius, or really with this equation to make it more general, I would say distance from center. Maybe that's a better way to do it. The unit on that, since we're only using standard units, I'm not going to have any metric in there, will be inches. And the last one is this J value. J is called the polar moment of inertia. And the units on J would be inches to the 4th power. And that is another equation. Remember, it's just a resistance to twisting, but we do have an equation. We basically have two, depending on if it is a solid shaft, right? So if it's solid, then our J is equal to pi over 2 times the radius to the 4th power. Sticking with this idea that radius is the distance from the center to the outside. The other option would be if I have like a pipe or a cylinder of some shape. Now I have two radiuses. I have an inside radius and an outside radius. So because of that, I have to include that within my polar moment of inertia, but it's the same equation, pi over 2 times the outside radius to the 4th minus the inside radius to the 4th. Now, I did give this equation in the notes in terms of diameter. Feel free to use that, but I'm trying to keep this as simple as possible, so I'm only doing one equation with the radius so you don't accidentally screw it up and make a simple error, right? So that's what we covered for torsion. Let's move on to our other stress, our bending stress. So we just did torsion, twisting, now we're doing bending. And we said with this bending, what we have is compression on the top, tension on the bottom. So this is what I'm showing here. In this case, we're saying if I had a point load, and I were to zoom in on like a cross section of that beam right there, I don't want it to look like a crack, but if I were to analyze what's going on internally and blow it up, I have something that I see down here where I have compression on the top. My maximum stress is in compression on the top, and my maximum tensile stress is on the bottom. In the middle, we call that the neutral axis, where there is zero stress, and we have a y as the distance either up or down from that neutral axis. So our equation we came up for that stress was the following. We said that sigma is equal to my over I. Now sigma is the same variable we used for axial stress when we were in tension or compression, so it makes sense that we would have the same variable now. With this, we have sigma represents our stress, and the units will be just like before, either PSI or KSI, and it just depends on that force up here. Was this in some pounds or was it in kips? And that will determine if you have PSI or KSI, just keeping your units consistent, right? M is our moment, and the unit on our moment, it should be in either pound inches or kip inches. So once again, just keeping with either pounds or kips, but make sure you get that little inches in there, because a lot of times when these problems are given, and this was on the quiz as well, this dimension might be like 10 feet, right? You could convert it in the very beginning and call it 120 inches, or just at some point when you get to that moment, you need to convert it over to inches, right? Because we want to be everything in pounds and inches or kips and inches to make life a little easier. So that's, then we have our y. Our y is that distance from the neutral axis, and the units on that y should be in inches. Usually the y should be right at the center of your beam, right? Everything we're going to do in here will have the y at the center, or the neutral axis at the center. And so if you're looking at the worst case scenario, it's always just your total depth divided by 2. And my last variable is I, which is a moment of inertia, and its unit would be inches to the 4th power. So let's talk about how to find these particular values. So let's first start by how we're going to find the moment. And for this class, all you have to be concerned with is 2 different cases. They're probably the most common cases that we'll have in real life anyways. So the first case is if we just have a single point load right at the midpoint of the beam. So if I had a beam supported by walls or columns or something on each side, and I put a point load, I'll call it P, right at the midpoint, and the total beam has a total length of L, then my maximum moment, which is what I care about, is going to be equal to PL over 4. The magnitude of the force times the length of the beam divided by 4. And we saw that in some tables. You could go back to your notes and actually look that value up if you wanted to, or see where the diagram comes from, right? The second type of moment that we should be concerned with is a distributed load over the entire beam. So graphically, what that would look like is I have my beam, and my load is the same all the way along this beam. So those would be values of like, and it's labeled as a W. Those would be values of like kips per foot or kips per inch over that beam. And then we have the same over all the length of the beam. And in this case, our moment would be equal to that load, W, times L squared over 8. So really, on problems like this, what you're trying to do is you're trying to identify the type of load. Is it a point load? Like on the quiz we had a construction worker standing on a 2x4. Well, that would be a single construction worker standing on 2x4, so it's just like a point load. This would be more like if I had, it would have to be given in a way like the load is, 8 kips per foot or something like that along the length of the beam. And then it's just a matter of identifying the length of the beam and squaring that, multiply it to W, divide by 8, getting that maximum moment, right? The other new variable here is this idea of moment of inertia. We had polar moment of inertia. What polar moment of inertia is resistance to twisting. Moment of inertia is resistance to bending. But background aside, the only cross-section we're going to have in this class, which is once again probably the most important, is like a rectangular cross-section, right? Like a 2x4 or a 2x6 or something like that. And it'll have some base dimension and a height to it. And if that's the case, then our moment of inertia is equal to 1/12 the base times the height cubed. And our last concept is just an overview of concrete. With concrete, what you should be familiar with are the components of concrete. So you have aggregate, you have Portland cement, you have water, or some other additives. And then be familiar with properties and variety of those components. So similar to the quiz when I think there was a question about for the greatest strength, what shape and texture aggregate would you have? Questions like that. You should be familiar with what hydration means. And if you forgot, hydration is the reaction of the water in the cement. So it's a chemical reaction, and it's an exothermic chemical reaction, meaning we have this thing called the heat of hydration, which is, it means it's actually putting off heat. And also particle size. So there was a little discussion about how particle size affects the hydration process and things like that. So, also know about slump testing, the process of slump testing, and what it means. What does a larger slump mean? What would we expect for stiff mix versus a very workable mix? Know about concrete strength. And there's two ways that we were looking at concrete strength. One is in compression, which is where concrete shines. It's mainly used for compressive stresses, right? But also in flexure. So in flexure, using those same principles we talked about earlier, where we have this distribution, concrete cannot handle tension, so we add rebar, right, to provide that, or some kind of steel. So that's the last topic you should be familiar with. And also this idea of pre-stressing and how you can have pre-tensioned and post-tensioned, and it's both part of pre-stressing. So that's it. Go through your notes, get organized. Hopefully it's not too bad. Let me know if you have any questions as you prepare for this, or even during. You can always shoot me an email. I can't give you actual answers, but I might be able to help you out if needed. And good luck, and I'll talk to you all later. Thanks.